Section 1.4 about solving inequalities. I told you in class I would never ask you to graph just x equals 3, even though in one of the previous sections they asked you to graph x equals 3. And so as difficult as that is, you plotted a point on 3 and you called it quits and you moved to the next question, because that's as difficult as it was. Well, what if I asked you to graph x is greater than 3? Okay, now I want you to graph numbers that are bigger than 3. Well, it's true that I can graph 4 and 5 and 6 and 7 and every little decimal in between. And I get so sick of plotting points that instead of doing that, we draw a solid line in one direction. But if I do not want 3, I've got to indicate somehow on the line that I only want the values that are bigger than 3. So I put an open circle, okay, and then I'm going to the right because those are the values bigger than 3. And so because I'm so sick and tired of plotting points, I will just shade the whole thing one direction. Obviously, x is less than or equal to 3. We're going to have a closed circle on 3, and in this case, arrow to the left, indicating you want everything lower than 3 or equal to 3. Okay, so that's all well and good. And then in the book there are some properties. I'll just show you briefly. The way I can get them easily for you to see. So we got the transitive property. That's pretty easy. A is less than B. B is less than C. So A has to be smaller than C. Well, that's pretty plain. Pretty easy to understand. Addition property. If A is less than B, you could add something to both sides. It's just like an equation. You can add the same thing to both sides. You can subtract the same thing from both sides. But when we get to the division and the multiplication, something is different. You can multiply and divide on both sides of an inequality. The difference is when you multiply or divide by a negative number, the sign switches. I am talking about the sign of the inequality. See, it goes from less than to greater than, less than or equal to, greater than or equal to. It has everything to do with the fact that the multiplier was negative. And that works for multiplication or division. Okay, so in example 1, we have 3x minus 12 is less than 3. We want to solve and graph. Solve and graph. Well, it's not too bad. We're going to add the 12. We're going to get 15, right? Because we're going to add the 12. And then we're going to divide by the 3. Did I have to switch the sign? Absolutely not, because I did not multiply or divide by a negative number. Now, it's never a bad idea to let yourself think about that. Open circle, arrow to the left. We'll have some questions like that where we have to do some solving, and then you have to decide whether you're going to have an open circle or a closed circle, and we're not going to end up doing B, so I'm thinking those are pretty straightforward. So we'll jump to example 2. Once again, solve and graph. So we get, 2x minus 3 is greater than 2 times x minus 5. Of course, we're going to have to use the distributive property. We've got a 2x minus 10, and over here we got a 2x minus 3. Of course, we push the variable terms to the one side, and we push the constant terms to the other side. And so we're going to get rid of all the x's. Well, that's kind of weird, isn't it? If I move this to the other side by adding 3, right? We get 0 is greater than negative 7. So here's the question. How often is 0 bigger than negative 7? Is it Always true, sometimes true, or never true. 0 bigger than negative 7. Isn't that always true? And if that's always true, then that means that x doesn't matter. No matter what x you pick, this is always going to be true. So, what do I put on my number line? I mean, I'm supposed to like graph this thing, right? What am I supposed to do? Shade the whole number line. Another way to say that is all real numbers. And we did use that notation in class. And so I'll just show it to you again, that R with that extra bar in it. That means the same thing as all real numbers. Because anything works. Well, example B here, 7x plus 6 is less than 7 times x minus 4. Of course, I'm going to do distributing 7x minus 28, 7x plus 6, and I subtract 7x's. And so this is going to be similar to the last one where we end up losing all of them, all the x's. And so we have 6 is less than negative 28. How many times of your life has 6 ever been less than a negative number? Never. So this is never true. You can't find a number on the number line that does work for this equation. No real solutions. There's nothing. There's nothing you could put on a number line either, because there's nothing on the number line that would work. No real solutions. Okay? In example 3 says the band agrees to play for $200 plus 25% of the ticket sales. I don't know what the ticket sales are, but the band is going to get 25% of that. They are also going to get $200. So 25% of the ticket sales and $200. The band has a goal of getting at least $500. At least $500. So move the 200 to the other side. Right? We know we're going to be subtracting it. It gives me 0.25x is greater than or equal to 300. Divide out the 0.25, divide out the 0.25, x is greater than or equal to 1,200. 1,200 tickets. At least 1,200 tickets in order to make their goal. Now, that's not necessarily true. It's $1,200 worth of tickets. In other words, if each ticket was worth $5, obviously it's not 1,200 tickets. So you could calculate that by dividing 1,200 divided by 5, or each one's worth 10. Obviously, that's an easy one, 120. If it was 5, we'd need 240. So you'd have to do a little bit of thinking there to come up with the number of tickets, but obviously if they're all worth $1, then yeah, I need 1,200 people, at least. Okay, the next thing we need to talk about is called a compound inequality. And in the compound inequality, The compound inequality is going to use one of two different words, and, or the word or. A compound inequality, just like a compound sentence, is when you put two different sentences together. This would be mathematical sentences, and we use one of these conjunctions, one of these connecting words as they use in your English classes. Now, one of these means the and is talking about the intersection, okay, or the overlap. The other one, sometimes we use the word union. It basically means putting all the pieces together. Now, when I say that, I don't mean if you have the number 5 and the number 7 that you add them together and get 12. I mean you list them all out, 5, 7. It doesn't mean I'm adding up numbers together. I'm just putting all the elements in the set. Okay? So, for instance, if I had a group of numbers, I'll just use parentheses, 2 and 3, and another group of numbers that was 1, 3, and 4, and I said, what happens if you take 2 and 3 and 1, 3, 4? Okay, so in other words, I'm asking you to identify every value that is in common to both sets. Overlap. Maybe I should use the phrase in common. Is there any number that's in common? Well, sure. That would be the number 3. But if I ask you the question, list all the numbers that you see in both sets. I'm not adding the numbers 1, 2, 3, and 4 together, but if I were to go through and start putting all the pieces together, well, I see a 1 here, I see a 2 over there, I see a 3 in both sets, and I see a 4 over here. This is the group that's called the union, or, ironically we use the word or, I'm putting all the pieces together. So overlap, putting all the pieces together. Now, we're going to do that with much bigger sets, so we won't be identifying them by individual numbers. I just wanted to give you an example of something small to work with that might make more sense. So example 4 says graph the solutions to 3x minus 1 is greater than negative 28 and 2x plus 7 is less than 19. Whoops. Too high up, you can't see the instructions. Okay, so I'm going to add 1 to both sides, giving me 3x is greater than, I put the plus 1 over here, and that would give me negative 27. Divide by 3, divide by 3, x is greater than negative 9. So should I have flipped the sign right there? Is that one of those situations where I'm dividing by a negative number? Just because there's a negative number involved. Yes, I see a negative 27. It's this number that I'm paying attention to, the number that I'm dividing by, and it's positive. So no, don't change it. Over here, we're going to push that to the other side, subtracting 7, giving 2x is less than 12. Obviously, we're dividing by 2 on both sides. Once again, that number is positive, so x is less than 6. And no, I did not need to switch the signs. Now, here's a number line. On one end, I got negative 6. On the other end, I got positive 6. I'm not getting into writing down a huge amount of numbers here, folks. Let's make our lives simple enough. Okay, we've got bigger fish to fry than how many numbers did you put on your number line? Above the number line, I'm going to actually do each individual part. So greater than negative 9, that's an open circle and an arrow to the right. Whereas less than 6 is an open circle and an arrow to the left. Obviously, you can see that these two groups are overlapping. Not every group is going to overlap. Some of them are not going to overlap at all. But this right here is saying, what do they have in common? Well, if you were to look at all these numbers and start identifying what they have in common, they have everything in common between negative 9 and positive 6, but not including the endpoints. How would this problem change? How would this problem change if the word was or? So if I asked you to identify all the values that were in x is greater than negative 9 or x is less than 6, and you had to start writing them all down, keep in mind that one goes on forever and ever to the right, one goes on forever and ever to the left. Do you realize every number would be accounted for on the entire number line? So we'd be highlighting everything with arrows on both ends. This would be an all real number situation. Every number got covered. When you started thinking about all of these, they would hit all the positives, and all of these would hit all of the negatives. You got everything covered. Now, what they have in common is only in the middle. But what you have when you put them all together is everything. Okay? Example 5. So we want to graph this. And so, of course, I'm adding the 2 over to that side, giving myself 16, and I'm dividing by positive 4. Since that's a positive number, I'm not switching the sign. And I'm adding the 4, and I've got 3y is less than or equal to negative 9, and I'm dividing by 3, and since that number is a positive number, oops, I do not switch the sign. So I've got negative 3 here, and I got positive 4 there. So greater than or equal to 4, so I'm going to do this above the graph before I actually put my final answer on the number line. So that would be a solid dot because of the equal to part right there, and I would shade to the right. And this would be a solid dot, and we're going to shade to the left. Or means to put all the pieces together. So take all of these values from this one and all of these values from this one and put them in one group. So that's my final answer. How would this be different if it was an and? So if it said y is greater than or equal to 4 and y is less than or equal to negative 3. Alright, so we're graphing, we got a negative 3 and a positive 4, and you see that it's greater than or equal to this way, greater than or equal to, or less than or equal to that way. Whoops. Need to make sure you can actually see it. This is all about what they have in common. I don't see that they have anything in common. They have nothing in common. There are no solutions to this. Nothing. There's nothing in common. The graph has nothing in common. So you could end up with situations that have all the numbers on the number line, or you could end up with things that have no solutions at all. It just depends on what word they're using in between. Or, and. Okay, we'll talk about more of those examples. As you're doing homework, you'll see more and more of those. Okay, so in example 6, okay, quality control, sometimes they call it QC. Quality control is something that is you'll see in every manufacturing plant in the United States and all over the world. It used to be that people would just make parts and, well, it doesn't take you very long to figure out that when you're using machines to do things or people to do things, you'll find out that you could be making a bunch of things incorrectly and wasting a bunch of money and a bunch of time. And no business that I know of wants to waste money and time. Okay, they're trying to maximize profit and they're trying to reduce their costs because they want to be profitable. Their owners want them to be profitable, unless they're a publicly traded company, and then their shareholders want them to be profitable. You as a company want to be profitable because you want to keep your job. Everybody wants that to be true. So in this particular example, it says the plans for a gear assembly, so in other words, they're making a certain part, specify a length of 13.48 centimeters. Okay, so this particular part that we're making, if I could make the part perfect in length every single time, the perfect length would be 13.48 centimeters. But you know and I know that nothing is made perfectly the same every single time. Machines change, people change, and sometimes we make things longer or shorter than that. This would be absolutely perfect. Well, they also talk about something called tolerance. Tolerance is what we are willing to accept as an error. Suppose I would be willing to accept a part if it was 3/100ths bigger than 13.48 or 3/100ths smaller than 13.48. Okay? So anything in that range would be fine. So in reality, I would be willing to accept the part if it went down to 13.45 or if it went up to 13.51. Right? That is down 0.03 and up 0.03. Okay, suppose we had a part and we measured it and it was 13.67 centimeters. We obviously know that's too much. Okay, my job as a machinist was to go in and take the part and cut it down so that it was the right amount. How much can I cut off so that I get it to be acceptable? Well, I'm going to cut off a certain amount, and it better be, when I get done, it better be somewhere between 13.45 and 13.51. It's got to be somewhere in there in order to be good. So the new part minus what I'm going to cut off has to be greater than or equal to this, and at the same time less than or equal to this. Now, I don't know if you realize this, but this right here is a compound sentence using the word and. I could really write this out in two separate things and use the word and. I'm not going to because I don't need to. So, how much do I need to cut off from every one of these? So subtract 13.67, subtract 13.67, subtract 13.67. I don't know if you realize what I'm doing, but I'm subtracting from the left and the middle and the right of this inequality, all at the same time. And so we end up with, on this side, negative 0.22 is less than or equal to x, or I should say negative x, which is less than or equal to negative 0.16. What should we multiply by to get this to be gone? Oh, yep. Multiply the entire equation or inequality by negative 1. Alright, so when I take negative 1 times negative 0.22, I get 0.22. When I take it times negative x, I get positive x. When I take it times negative 0.16, I get positive 0.16. When you're multiplying by a negative number, signs must switch. So the amount that I need to cut off as a machinist has got to be somewhere between 0.16 centimeters and 0.22 centimeters. Somewhere in there, I'll have the value that I'm looking for. Okay, we'll practice those. The quality control example, you won't have like tons and tons of those, but it's an example of a compound inequality that you see in real life.